Can a one-dimensional curve completely fill a two-dimensional space? It sounds impossible, but in topology, it's actually true. Today, we explore space-filling curves and the concept of compactness in metric spaces. In standard geometry, dimension is a rigid property. A line has length, a square has area, and no amount of folding allows a one-dimensional object to cover a two-dimensional surface. Topology reveals that continuous surjections can manipulate dimension in ways that contradict standard calculus intuition, allowing a mapping to cover every coordinate in a higher dimensional target. This specific phenomenon is known as the space-filling curve. Because visual intuition fails to account for these infinite iterations, we must rely on rigorous definitions and logical proofs to navigate the material found in competitive exams. To prove this isn't a mathematical trick, we need the specific tool used to handle infinite sets, compactness. We will break down sections 44 and 45 of Munkres to extract the exact properties needed for exam-level proofs. Compactness allows us to treat infinite topological spaces as if they possess the restrictive, manageable properties of finite sets. Our paradox operates by mapping the unit interval 0, 1, a line, to the unit square, 0, 1 times 0, 1. The existence of this map depends on continuous surjective functions, which ensure that every point in the square is reached by the curve. It is important to note that a continuous surjection does not automatically preserve the dimension of the domain. To prove how a one-dimensional line covers a two-dimensional square, we must first establish the specific properties of metric spaces. A space-filling curve is defined as a continuous surjective function from the unit interval to the unit square. We can visualize this through iterative paths, f1, f2, and f3. Each step creates a more complex piecewise linear path within the square. As the maximum distance between these iterative paths shrinks, we arrive at the concept of uniform convergence. If a sequence of continuous functions is uniformly Cauchy, the resulting limit function f is guaranteed to be continuous. Because the unit square is a complete metric space, this limit f is guaranteed to exist within the target domain. If the domain meets certain criteria, the image of the function will densely cover every coordinate in the square. The construction of this curve is predicated on a specific property of the domain, compactness. To understand why, we must establish exactly what it means for a space to be compact. In section 26, Munkres provides the formal topological definition of compact spaces. A space is compact if every open cover of that space contains a finite subcollection that also covers the space. Imagine a set covered by an infinite number of overlapping open circles. If the set is compact, we can remove almost all of them and still keep the entire set covered with only a finite number of circles. This is distinct from limit point compactness. Under this definition, every infinite subset of the space must possess at least one limit point. Finally, we consider sequential compactness. This requires that every sequence of points within the space has a subsequence that converges to a point inside that same space. In general topological spaces, these definitions are distinct. A space can satisfy one while failing the others, requiring separate proofs for each specific condition. However, these disparate definitions align when we work within metrizable spaces. Munkres theorem 28.2 provides the link between these concepts. The theorem proves that in a metrizable space, compactness, limit point compactness, and sequential compactness are equivalent. We can demonstrate this equivalence using the logic of the Lebesgue number lemma. Distance metrics, represented by epsilon balls, provide the mechanism that connects abstract open covers to discrete points in a sequence. If a sequence lacks a convergent subsequence, every point can be isolated within its own epsilon ball. These isolated balls form an infinite open cover that cannot be reduced to a finite subcover, proving the space is not compact. Because metric spaces collapse these three definitions into one, they provide an air-changeable toolkit for advanced topological proofs. We can test this framework by applying it to a common exam problem. In a standard metric space like the real numbers, the closed interval 0, 1 is a compact set. Contrast this with the open interval 0, 1. Consider an open cover of intervals un equals 1 over n, 1. They expand to cover the space. Taking any finite subcollection forces us to stop at a value, 1 over n. This leaves points between 0 and 1 over n uncovered, meaning the space is not compact. This demonstrates how the specific boundary conditions of a set dictate its topological nature. This logic helps avoid a common error found in competitive exams like CSIR Net and JAM. Many students incorrectly assume the Heine-Borel theorem, that closed and bounded sets are compact, applies to every metric space. The theorem is valid in Euclidean spaces like Rn. However, it fails in infinite-dimensional Hilbert spaces or discrete metric spaces. In a Hilbert space, the distance between basis vectors is the square root of 2. Even though the set is bounded, the points cannot cluster, making a convergent subsequence impossible. The construction of a space-filling curve is possible because continuous functions can map compact domains to dense targets. Metric spaces are unique because they allow us to use sequences, limit points, or open covers interchangeably to prove this property. If you found this explanation helpful, don't forget to like the video and subscribe for more book-based mathematics explanations.